Okay, in this video, I'm going to look at what is called Stokes theorem. So this is basically an extension of Green's theorem to 3D space. So Green's theorem is actually referred to as Green's theorem in the plane. So it is in 2D space. So this theorem here extends the idea of Green's theorem to 3D space. So if S is a positively oriented surface bounded by a simple closed curve C with positive orientation, and F is a vector field whose components have continuous partial derivatives on an open region in R3, this region must contain S, so S is a subset of the region. So basically the partial derivatives of f are continuous throughout S. Then this contour integral of work done around in moving a force, an object around C, is going to be equal to the double integral over S of the curl of f dot ds. So what's happening this time is basically we have, and if you imagine, we have something like this. So this is our surface here, and then its edge is going to be the contour C. So again, as we traverse along this, we want the surface to be on our left hand side. So this is going to be our contour C. We're not going to prove this theorem, but we're just going to go straight into examples and demonstrate how this theorem works. Okay, so in this example we want to verify Stokes theorem for the case where C is the curve of intersection between the plane y plus z equals to 2 and the cylinder x squared plus y squared equals to 1, and f is given by this expression here. So in cases of verifying, as we mentioned in the previous section, we're going to have to work on the left hand side, work on the right hand side, and show that those two are giving us the same value. So first point of contact here is going to be to make a sketch of the situation. Right, so first of all, we've got a cylinder x squared plus y squared equal to 1. So that means if z does not appear, means that our axis of the cylinder is along the z-axis, because actually this thing is going to be a circle on the xy plane, and then you just extend it in both ways. Okay, so that means we're going to have something like that, but yeah. So there is our there is our cylinder extends this way and up that way. And then there's going to be the plane. So the plane y plus z equals to 2. So it means when z equals to 0, it's going to, sorry, when y equals to 0, z is going to be 2 somewhere there. And when z equals to 0, actually y is going to be negative 2. So that means it's going to be slanting the other way around. So we're going to have a plane. It's going to be a bit difficult to sketch. So we've got a plane that looks something like this. Okay, this is I'm going to draw it wrong, just for the sake of the ease of drawing it. Okay, so I'm going to draw a plane that is slanting this way. So I'm going to draw a plane that is slanting this way. Okay, but actually this plane is going to be slanting the other way. And then so it's slicing this cylinder somewhere there. So we're going to have a an elliptic type of curve there, and this is the region we're actually interested in. Okay, so if we just remove everything else, we're actually even going to remove. So this is the situation we have. Okay, so let's remove this, remove that. Right, so that is what we're interested in. So that is our R there. So that is our R there, and that is going to be our C. Okay, so so first of all, we're going to need to work out the contour integral of f dot dr. So that means for our C, we need to write a position vector. So remember the we've got the plane y plus z equals to 2, and then we've got x squared plus y squared equals to 1. So it's the intersection of these two. Okay, so this we can parameterize using trigonometric functions. So this cylinder is x equal to cosine theta, y equal to sine theta, because r is 1. Okay, so the contour here, C, we can parameterize as follows. So x, y, z. Okay, z is we can write in terms of y. So that is 2 minus y. And then using this parameterization, x is cosine theta, y is sine theta. This is 2 minus sine theta. So that is our r. So that means dr is going to be, the derivative of this is going to be minus sine theta cos theta here, and minus cos theta there, d theta. Okay, Then the next thing we're going to need to write the force field in terms of the parametric coordinates. So y squared is going to be negative sine squared. That is cosine. That is going to be minus 9 cosine. So f is minus y squared x minus 9x. So y is sine squared. So this is going to be minus sine squared theta cos theta. This is going to be minus 9 cosine theta. So that is f. So that means this contour integral f dot dr is going to be integral from 0 to 2 pi, because it's just going to be an integral of theta now, minus sine squared theta cos theta minus 9 cos theta. So that's just our f here, dot dr. Well, dr is minus sine theta cos theta minus cos theta d theta. We just do this dot product here. This and this is sine cubed, so we're going to have okay, so this is going to be this and this is going to be sine cubed. That is going to be cos squared. That is going to be 9 cos squared. So we're going to have 10 cosine squared theta plus sine cubed theta d theta. Okay, and then this is just integration of trigonometric functions. I will not bore you with the details. So if you go through this as usual, this works out to 10 pi. Okay, so that is the first approach. The second approach is the double integral approach. So remember, we have got this region here. So now we're interested in the surface integral of this. So the parameterization is going to be slightly different this time, because we want everything from the origin. So at first we're just interested in the boundary, but now want everything. So in fact the parameterization for x is going to be r cosine theta, y is going to be r sine theta. Theta is varying between 0 and pi, and r is varying between 0 and 1. So in the earlier case, because we're just interested in the boundary, r was just equal to 1. But this time r is varying because it's the whole region. Okay, so that means our parameterization of the region is going to be x, which is cosine theta, y, which is r sine theta, z, which is 2 minus y, so this time is 2 minus r sine theta, and theta and r are varying as shown. So because this is a surface, so we have got a 2-parameter equation here. The parameters are r and theta. So as done before, we're going to do r and r theta, then we do the cross product. Okay, so RR is going to be just the derivative of this partially with respect to R, sine theta here minus sine theta there. The derivative of this with respect to theta now is going to be minus R sine theta, R cosine theta. This one is going to be minus R cosine theta. Then we are going to do R cross R theta. Okay, if we do that, as usual, it's going to give us 0 R. Okay, this is pointing out upwards because Z is positive. Which is not a problem. Okay, so then the other part of the integral is the curl of f. So we're going to have to do curl of f. We can do that in terms of Cartesian coordinates. Then once we've got the curl, we are going to then convert to polar, or those parametric coordinates. So this is going to be 0, 9, 1 minus 2y, which in terms of those parametric is going to be 0, 9, 1 minus 2r sine theta. We are now ready to plug into our right hand side. So we've got curl of f dot ds. So this is now going to be double integral of r and theta. So the curl is 0, 9, 1 minus 2r sine theta. ds is 0 r. Then we're going to have dr d theta. R goes 0 to 1 theta, 0 to 2 pi. If we multiply out here, just do the dot product, it's going to be 9r plus r minus 2r squared sine theta dr d theta. So this is actually 10r minus 2r squared sine theta. This integral is not exactly difficult. Actually, we can split the r and theta integrals. So this one, 10r is going to be, so if we just do 0 to 2 pi d theta, then 10r dr 0 to 1 2r squared sine theta 0 to 2 pi d theta. Here we're going to have 2 pi. This one is going to be 10r squared over 2, 0 to 1. That is going to be 2r cubed over 3. 0 to 1 integral of sine is negative cosine theta 0 to 2 pi. And so we do the calculations. This is going to be 2 pi times 5, which is 10 pi. Cosine theta between 0 and 2 pi is going to give us 0, so the second term is going to contribute nothing. So that is the same as the integral which we did earlier. Okay, in this number 2, use Stokes theorem to evaluate this double integral over S, where S is the part of the sphere, x squared plus y squared plus z squared equals to 4. Inside the cylinder, x squared plus y squared equals to 1, and above the xy plane, and f is given by that. So first thing to do here is to make a sketch just to get a picture of what's happening here. So first of all, there is a sphere of radius 2. Okay, so something like this. And then there is a cylinder of radius 1. Okay, cylinder of radius 1. So this is going to intersect with the sphere. So we're going to have a so that's going to be like the surface. Yeah, my sketch is a bit wanting. So what's going to happen is where it touches this. Yeah, okay. So the surface of interest is going to be this one here. Okay. If you take this and plug it here, it's going to give you z squared equals to 3. So that means here z is root 3. So we've got something like this. Then that's going to be our contour. Okay. At height z equals to root 3. Of course, the radius is 1. So it turns out that it is going to be easier to do the line integral of that thing rather than the double integral. So that's the whole point of use Stokes theorem. As an exercise, you will want to do the double integral and actually confirm that you find the same answer, and it is much longer than the one we're going to work on here. So it's exactly at z equals to root 3. That means the parametrization is going to be x, y, z is root 3. Since it's on the cylinder x squared plus y squared, so the parametrization is going to be cosine theta sine theta root 3. So dr going to be negative sine theta cos theta 0 d theta And then the function f here, in terms of the parametric coordinates, yz is going to be root 3 sine theta minus xz is going to be negative root 3 cosine theta. Xy is going to be sine theta times cos theta. So that's going to be our f there. Then if we so the contour integral f dot dr, so if we do the dot product of this and this, of course theta is now ranging between 0 and 2 pi. There's going to be this, which is sine squared, this one is cos squared, this one is 0. So so that thing is just going to be negative root 3 sine squared theta plus cos squared theta d theta, which is just integral of root 3 d that. So that's going to be minus 2 pi root 3. Okay, so it brings us to the end of Stokes' theorem.